welcome Mr. Darshan Kumar Pandit, who is the founder and principal engineer of Synchronous Drives and Inverters Private Limited. Darshan sir is an entrepreneur, and he was born in Vadodara, Gujarat, and he received his bachelor's in electrical engineering from C.K. Pitawala College of Engineering and Technology in 2006. He did his MTech in Power Electronics and Electric Machines and Drive from IIT Delhi 2014. Sorry. He has secured among first 1% to 2% rank thrice in GATE. It's a quite an achievement. You can understand that. All India rank 96 in GATE 2012. From 2006 to 2007, he was working with SVNIT Surat as a teaching assistant. And from 2007 to 2012, he was working with Reliance Industries Limited, Hazira, as a maintenance engineer. He pursued his master's from 2012 to 2014 from IIT Delhi. From 2014 to 2018, he has built electric and hybrid electric vehicles with Engineering Research Center at Tata Motors, Pune. From 2018 to 2024, he has been working with MATLAB, as you all are familiar with, writing software for electric and hybrid vehicle domains. At present, he is building an EV startup, Synchronous Drives and Inverters Private Limited, and it is supported by SVNIT Surat and FITT IIT Delhi. So we welcome Darshan sir. He is vastly experienced in different domains. So I believe that his lecture will give a great insight to you, and it will be very useful for those who are pursuing some kind of a research in EV specifically. So Darshan sir, we may start.
Okay. Am I audible now?
Yes.
Hi, yes.
Okay. Yeah, we can start. Let me share my screen and we can start. And how much time do we have?
Till 9.
Okay.
That is 1.5 hours.
Okay, yeah, that is fine. So we'll see how much can be covered in this time. Let me know when you're able to see the screen.
Yes.
Okay. So yeah, well, thank you for the warm introduction, Professor Chirag and Professor Ravi. I'm Darshan Kumar Pandit from Synchronous Drives and Inverters. We are a startup based out of SVNIT, Surat, and IIT Delhi. And we are trying to build the world's most efficient electric vehicle technology, both hardware and software. And that's where we are trying at the prototype level at the moment. And yeah, this session will be about electric vehicles. So that's there. Here's a professional journey, what Professor Chirag was trying to explain. So what I have been doing in the last decade is I already built world's most efficient electric car. Then we already built world's first algorithms for world's first more electric aircraft. India's first high power converter for fuel cell buses. We have 10 of them running in India. And India's first in-house motor controller for electric vehicles. This was with my time at Tata Motors, and then afterwards I have been building software for various electric vehicles used by almost all automotive companies in the world, Tesla, Toyota, Tata, and more. The software includes motor control block set and Simulink automotive products by MathWorks. So that's a brief, and this is the outline for today's session. We'll get started with an overview of the EV space and specifically what we want to develop, which is a PMSM control. And from there, we will. Okay, one guy is asking to join, so I'll just share the link. We'll go towards mathematical modeling, control system design, system identification, simulation and analysis, and code generation and deployment. I also have a demonstration at my desk here, but it might take us longer to go through that because I am still preparing that. But we'll see if we have time, we can do the demonstration as well. And I have to just forward this invite to the meeting. Sorry about that. Um, okay. Yeah, so yeah, that's an overview, and then we can take questions and answers. Or maybe you can take questions and answers first and then go for the demonstration since it is going to take time. So, as an introduction, motors are everywhere. We all know that electric vehicles have it. Apart from that, there is a lot of traction motors in railways as well as the suburb metro rail. There are electric compressors, air conditioners, power tools, and many medical devices. They use this motors. And what's different about them when it comes to automotive is that we can operate the motors in four quadrant operation as against the IC engine, which can be only operated in two quadrants of operation. These quadrants are mechanical or quadrants. If you designate one direction of rotation of a wheel as positive direction, let us say clockwise direction rotation of the wheel is positive, then any torque that forces the wheel to move in that direction, we can also put a convention that that torque is positive torque mathematically. And when both of these go together, the vehicle will supposedly move forward. It will propel forward, and that is called forward motoring, where speed is also positive and torque is also positive as per our convention. And power is a product of torque into speed. So the power is positive. When it comes to electric vehicles, power is stored inside battery systems, and electricity, when the power is positive, as per this convention, electricity is converted from electrical energy into mechanical energy output at the wheels. Then there is also reverse motoring where the wheel moves in the opposite or counterclockwise direction in this example, and the torque applied is also in the counterclockwise direction. Again, the power is product of torque and speed. So vehicle will move in reverse, but the energy that is still positive, which is product of torque and speed, and that means energy is still converted from electricity into mechanical energy. Then we have something known as forward braking, where the wheel is moving clockwise, but the torque is applied counterclockwise. In simple words, you are going downhill and you want to apply torque against the direction of rotation of the motor. You want to stop the vehicle from going downhill. That is applying brakes or maybe applying reverse direction of rotation from electrical motor. So doing that will require a product which is torque into speed, which is negative. And whenever this torque and speed product is negative, it is possible for us to convert the machine from motoring into something known as generation region, or we can also apply all this energy into mechanical braking systems. So this region is known as forward braking or forward regeneration or regenerative braking. But we are essentially converting energy from mechanical input into electrical output. We can save that into batteries. And we also have reverse braking or reverse regeneration, where vehicle is going downhill but in reverse, and you want to propel it forward. So torque is applied positive and wheels are going in negative direction. So again, the product is negative. The energy is converted back from mechanical to electrical in case of reverse regeneration. Electrical motors allow us to switch from motoring to generation based on their inherent characteristics of energy conversion from electrical to mechanical and vice versa. Which is why what we call them is in general machines, not motors or not generators. And there are different types of machines. They operate on different principles which are fundamentally same, but based on operational principle, we call them DC machine, AC machine, and different types of machines are there. They are for electric vehicle industry. They are classified based on two basic factors. One is volume and second is weight. The lighter the weight and volume of the vehicle, the more it is suitable for electric vehicle applications. If it is too bulky, it might require a bigger vehicle like a railway engine, which used to use DC machines and are now getting migrated to induction machines. But for small car, small vehicle, we cannot use big motors. So for this machine, for this kind of cars, vehicles, what is getting popular is permanent magnet synchronous machine. And there is also another category called BLDC machines. And nowadays, there is also an increasing popularity of switch reluctance machine and synchronous reluctance machine. Each type of machine has its own complexity in operating, its own advantages and disadvantages. And primarily, as I said, weight, volume, and the third factor is efficiency. They are making them popular for different applications. We can classify the machines into a number of categories, and they are increasing as we speak. Every day, somebody is trying to invent a new motor, and we are seeing a drastic improvement of efficiency of machines starting from 50% going all the way to 96% when it comes to electric vehicle. And different types of machines are there: radial flux, axial flux, permanent magnet, assisted synchronous reluctance motors, and all these have complex operating principles. Today we are going to talk about permanent magnet synchronous electric machines, where we will be using permanent magnets to energize the field of the machine. And this can be DC as well as AC. Within AC, we are getting more efficiency, and the back EMF can be trapezoidal as well as sinusoidal. Whenever it is sinusoidal, the windings are distributed sinusoidally, and that allows us to produce torque uniformly. For BLDC, we have glitches in the torque generation. And within sinusoidal type of machines, there are two types of rotor arrangement. One is surface mount magnets and other one is interior mount magnets. So these are classified further as surface mount and interior mount magnet based of machines. The left one is the surface mount PMSM and the right ones are the interior mount PMSM. The interior PMSM has an added advantage that it also allows some reluctance torque, meaning that if the magnet gets demagnetized, still the machine is capable of producing torque based on reluctance machine's principle. However, reluctance torque in case of IPMSM is less compared to the electromagnetic torque, which is generated because of interaction of the magnetic field with the stator's rotating field. I'll explain what that is shortly. But there are some advantages and challenges of each type of machine. And as far as a vehicle is concerned, power electronics is used everywhere, and that is inside the battery called battery management system. There is e-drive system, also known as motor controller. There are auxiliaries such as DC to DC power conversion. We need to reduce the battery voltages such as 350 volts of battery voltages used in Tesla Model S and Model 3 into 12 volts battery voltages required by the auxiliaries such as headlights, side lights, indicator, the wiper, motor, the window shield and all. So that's where DC-DC converters are employed, and furthermore, different converters are there. Here is a simplified introduction of a traction drive. So what we do is primarily in motoring mode, we try to convert electricity stored in the battery into mechanical motion of the wheels. In the process, the control system operates the machine as a motor. It takes the feedback of currents as well as position from the motor, and it processes the user input, which is the accelerator pedal in this case, that is converted into reference torque by the control system. And control system processes this and generates some gate pulses. These gate pulses are fed to either MOSFET or IGBT based inverter, and the inverter converts the DC electricity into controlled variable voltage, variable frequency currents required by the motor. That leads to the exact required torque. And this is then given to the transmission, which is usually a single speed gearbox, and that moves the wheels. When we want to do generation, we apply the torque in opposition to the direction of motion of the wheels, and that generates electricity. We use that to store the battery, store inside the battery, if the battery is capable of storing the charge. We can also do independent generator control. So this is a concept which is getting picked up. By doing so, we can operate the IC engine at its maximum potential efficiency, and we can improve the efficiency of IC engine. And there is also a concept of range extended electric vehicle, where you can power an electric vehicle from battery as well as an IC engine. This is also similar to series hybrid electric vehicle concept. So where the same machine works as a generator and motor. Of course, there are two different machines, one for generator and one for motor for mechanical coupling with IC engine and wheels respectively. And if the battery is discharged, the IC engine can power up the whole system and vice versa. In some cases, the IC engine is replaced by fuel cell, so we call that fuel cell hybrid electric vehicles such as fuel cell buses of India. And in some cases, there can be a CNG machine. So that is briefly the concept of the inverter. Now, in simple words, how do we convert this energy flow? So, if we take a simple concept of a DC machine or a BLDC machine, here is how the current will flow to produce a positive torque. Two switches out of the entire six bridge will work at a time. And whenever we want to generate positive torque, we want to make the current flow from winding A into winding B. And that is how these switches will conduct in this schematic. So this gate pulses will be fired. But when the current flow through winding in A and B reverses, then the same machine acts as a generator. And instead of those switches, the anti-parallel diodes will conduct, and the current flow at DC link also will reverse. For DC link, the power is represented by product of VDC into IDC. So in this case, that power is negative. That means it is working as a generator. And positive speed, so again, we go back to this theory where current is flowing into the motor A phase winding. But if we want to change the direction of rotation of the wheel, provided we have the position information, then this can simply be achieved by changing the phase, active phase from A to B phase. And this way we successfully manage to reverse the direction of current from the motor winding. However, the current coming from the battery is still in the same direction. So the power flowing from battery is still positive and electricity is still converted from electricity to mechanical energy while reversing the direction of rotation of the machine. And then there is a fourth case, which is reverse regeneration, where we reverse the direction of rotation, and the antiparallel diodes of Q3 and Q4 switches will conduct. That is not shown here. When we want to implement this motor control algorithm for electric vehicles, we also see a lot of developmental challenges. These are majorly categorized between modeling and simulation at the system level, then control system design, then embedded system programming. A lot of embedded systems are there, and then implementation on the real world hardware. Some of these challenges are explained here. First one is like we require the accurate rotor position of the permanent magnet motor, and this is achieved via some sensors, which are Hall sensors or quadrature encoder sensor, which is illustrated here. And then there are some machine characteristics we have to adopt to. They are not exactly as per theory. So we have to identify these machine characteristics and then operate the machine at that operating point. The traditional control theories such as field-oriented control or direct torque control also have limitations which require modifications by additional control theories such as maximum torque per ampere or unity power factor or constant torque angle control, constant state of flux angle control depending upon the type of motor, which is IPMSM in this case. So we have modified field-oriented control. And then there is something called field weakening. So there are four types of field weakening which we need to implement. And by implementing these different algorithms, we are ensuring that the machine always operates at its maximum efficiency point. The copper losses are same as core losses, and machine also operates at a speed higher than the rated speed while trying to maintain this energy balance. That is just discussing some of the challenges. Now, when we want to start development, how do we start? The first is systems engineering. We need to understand the system. In order to do that, we have to convert the entire real system into a computer model. So that is what we are going to do. But in order to understand that, we will have to understand some concepts from signals and systems. So that is what I'd like to cover here. In case the students are from not from electrical engineering background. So in electrical engineering, voltages, currents, flux, there are many quantities which are sinusoidal and they are time varying sinusoidal. So it's not possible to plot them easily because at every moment of time, this rate point changes its amplitude. So it's difficult to process this information as long as it is time varying. And what we do in electrical engineering is we change this complex sinusoidal waveform from real world into something known as mathematical space. And within that, there is a vector which is denoted by this light blue arrow. That one vector, when it is considered rotating in counterclockwise direction at a frequency that is known as the electrical frequency of the vector. This mathematical space can represent the real world physical quantity such as voltage or current or flux. So one light blue vector rotating in counterclockwise direction, which is conventionally positive for electrical engineering, can be decomposed into one phase, two phase, three phase, or n number of phases of components. And we managed to convert the sinusoidally time changing quantity into mathematically rotating vector in mathematical space. Now, what we are going to apply is this theory by Albert Einstein of general relativity for electrical engineering in order to control our motor. What is a theory of relativity? I think everybody is familiar with that. If you are at a station and if you see a railway moving, train is moving, then you will see that moving. If you are inside the train, you will see the station moving. If you are inside another train that is at the same speed as the first train, then you will see the second train as stationary. Now, all of these concepts that we learned at school, they are applied in linear motion. The train always moves in one line. And we are going to apply that into rotational motion for electrical engineering. So this space vector, which I was describing before, the left blue vector, which is rotating at counterclockwise speed, is what we are going to put inside the general theory of relativity. And how we are going to do that is that we will first of all reduce the complexity of system from three phases to two phase, which is possible mathematically using a transformation known as Clark's transformation. So using Clark's transformation, it is a simple mathematical trigonometry transformation where three-phase quantity can be reduced into two-phase, which are minimum required number of phases to determine the direction of rotation of this vector. And now this becomes easy to convert. What we are going to do is we are going to change the reference frame because it is time changing quantity. We are required to change the reference frame. And how we do that is instead of looking at a light blue vector here on your screen, close your eyes and imagine a fan above the ceiling above you. And we have all done this in our childhood. We have looked at the fan and we have tried to rotate ourselves at the speed of the fan. So we are just going to do this mathematically here. So you are rotating this light blue vector is a fan's blade and you are going to rotate yourself at exact same frequency of this light blue vector speed. What happens when you are seeing that at that speed, when you are moving at the same speed of the fan becomes stationary. And that is what is called change of frame of reference. So a fan which is moving for others will appear stationary for you. You can see the fan blade stationary. Mathematically, what we do is we apply the same concept, and that is known as Parkes transformation, where the axes which were stationary earlier are now rotating. So now the vector which appeared rotating to you in the stationary reference frame, which is what was earlier when nothing was applied, that becomes a rotating reference frame. And in this case, it is rotating exactly at the same speed of the fan, known as synchronous speed. And when this happens, the projection of this vector on these two axes, which were time changing before, sinusoidally time changing quantity, becomes a constant DC quantity. By doing this, what we have also achieved is we have removed one quantity which Albert Einstein was successfully able to remove in physics, and that is known as time. So now we got rid of time, and then it's just a DC voltage or DC current or DC flux, and it's much easy to control DC systems. How do we implement that? So I have made all of these blocks. If you use MATLAB, you can find them inside motor control block set. All this math which I was talking about, it's already done. And you can use these blocks, or you can create your own. If you're good at math, you can create your own blocks, and you can just do this, measure the voltages or currents, feed them into Clark and Parkes transformation blocks, and read the position information either from a sensor or various sensorless techniques, and then try to implement a control theory. In this case, the control theory is field oriented control, where we are trying to control the D and Q axis currents. So which is what is in this middle blocks. There are two PI controllers, and then they will generate some voltage references. When we do inverse of what we did in terms of Park and Clark transform, that is called inverse Park and inverse Clark transform, then we get AC quantities back. In doing this, we can also apply a different modulation technique that allows us some more advantage in terms of utilizing DC link voltage. So that modulation technique is mentioned over here, also known as space vector modulation technique. Now, I hope there is no doubt until now. Now, okay, we were able to reduce the complexity of a time-changing quantity successfully, and mathematically we are able to do something that is controllable. But how do we control a physical machine? Because it's a big machine that is going to move our vehicle. In order to do that, we have to apply some differential equations. We have to represent the machine from real world system into a differential equation of physics that explains the behavior of the machine in dynamics. So physics converts that into mathematics, and now this set of equations, which is visible here, that represents the entire performance of a PMSM or interior PMSM. And the first two are electrical equations, the second two are the flux equations, and last two are mechanical dynamics equation. Since these are differential equations, it's going to be complicated to solve them. But if we manage to solve them, we can also predict the behavior of the machine in time. We can know that what will happen to the currents of the machine after maybe, let us say, 1 hour or 1 minute, and we can control the machine accordingly by applying a different voltage than what was expected. So we not only got rid of time, we can predict the future by means of this mathematics, and that can be done by implementing all of this correctly. So the equations which I was talking about, they can be converted into set of blocks, and we can execute something known as differential equation solver using various computer programs that will solve them, and that will find our solutions to this currents or speed of the machine. And you can create this kind of models using softwares like MATLAB. And the last part which we need for simulation is the converter. So converter also is nothing but 6 switches, which can be reduced down to 3 switches mathematically, and we can create a model for converter as well. So all these mathematical models are also there, and we can go to the next step. So we understand the system, we have a physical representation of system in differential equations, and we can reduce the complexity of the system from an AC time varying quantity into DC machine. Now DC machines are easier to control and we can apply different control systems. The popular one is field oriented control. There is also BLDC 6-step control. There is also direct torque control, and these all techniques get modified by different maximum torque per ampere techniques and field weakening techniques. So the exact implementation will carry a lot more complexity. But here is a simplified implementation of a field oriented control for a speed control system where there is a reference speed that is compared with a feedback speed obtained from a sensor. This goes into directly reference torque generation. If you are using a machine which is complex like IPMSM in this case, it will have MTPA control reference block which will compare the speed and torque feedback, and it will try to find the optimized set of D and Q axis reference currents. These are fed to further to more controllers for current D and Q axis currents. D axis represents the direct field axis where the permanent magnet flux of the machine lies. So what we are looking at is the north pole of the rotor axis when we talk about direct axis. And if you increase the D axis current, that means you are increasing the flux of the machine from stator, and you can increase the magnetization of the magnet. And in field weakening, we are supposed to reduce this working flux. So in that case, we give negative direct access current, and the PI controller or any other controller is supposed to follow that and implement that. Q axis current is generally responsible for production of torque on the machine, and that is what is the job of the controller, PI controller for Q axis current. In advanced algorithms like MTPA, both D and Q axis current combination of this work together in generating torque as well as field weakening. So that probably we will put outside the discussion here. What is seen is the D axis current is reference is made zero and Q axis current is just coming from the torque reference. These are fed to inverse spark transform and then later on converted into space vectors that are used to modulate the duty cycles of pulse width modulation signal of the inverter. Inverter switches this via these PWM duty cycles from the available battery supply voltage and feeds these PWM voltages into the motor. Motor has heavy inductance, so the currents going inside the motor will not be PWM current. The currents that will go will be sinusoidal currents, and these are sensed by the current sensors. We also require position information for correct implementation of this for electric vehicles. So there is a position sensor that processes feedback. However, inverter will have PWM currents, so that is about inverter switching dynamics. We can discuss that later. And position feedback is converted also into speed feedback. There will be some sensor blocks and there will be conversion from mechanical to electrical position. What we are controlling is electrical current and electrical voltage of the machine. So that is why we require electrical position. And that too, we require the exact north pole's position of the permanent magnet on the rotor, without which it is going to be super challenging to control this motor. Um, Coming back to the control system design. So we will get started. There are as you can see, there are multiple controllers. Usually there are four. Whatever is seen in this diagram are three controllers, two current controllers and one speed controller. There is fourth field weakening controller also, which is not considered here. So we'll get started with the inner loop, which is the current control loop, and then we will expand this to outer loop, which is the voltage loop. How do we decide the controller is the challenge here. First of all, when we look into the current loop, it's not that easy as it seems. There are reference currents compared with feedback, and there is a PI controller which will have 10 different implementations. Output of this PI controller is supposed to control the motor voltages, but it cannot because motor also has something known as coupling voltages, or you can say transformer EMF and the speed back EMF. So in short, the D axis currents will have an impact on Q axis voltage, and Q axis current will have an impact on D axis voltage. And this need to be removed in order to design the control system. So we can do that by going back to our physics. physics was just a set of differential equation. We'll take the first two equations out of it and we'll convert them from time changing quantity into S domain as step one. And then in this S domain, we want to linearize the system. In order to linearize the system, there would be this cross-coupling terms, omega e psi q and omega e psi d, which we can mathematically add inside our controller beforehand itself, so that this effect of system voltages gets negated. So that is why you see this addition or subtraction of omega e psi d and omega e psi q decoupling terms. So this allow us to get rid of this extra term from equation 1 and 2 in equation 7 and 8 when we go for Laplace transform. Once we are in S domain, it's all frequency domain. And it allows us to generate transfer functions of the new duty cycle into currents and new torque into speed. So over here we have our transfer function of ID to VD and IQ to VQ, and that is simplified here. Also, this tau d, this quantity is the stator time constant for d and q axis respectively. Mathematically, it is just L by R of the machine. So having said that, now we have a transfer function, the equation 9 and 10. For Q loop, it is equation 10, which represents the plant model for the motor. At least electrical dynamics are covered. There are also more dynamics of the system. We are sampling the current, so there is a sampling delay. We are holding some PWM duty cycle for at least half of the sample time. So there is a holding delay. Inverter itself takes some time, let us say half of sample time, to generate the new pulse width modulation from duty cycles into actual switching. So there is this delay. All of these delays are represented by some transfer function, which is single order delay, and then control algorithm will also take at least one sample time to execute all the inputs, feedbacks from inputs into the generated PWM duty cycle outputs. And all of this has to be controlled by our PI controller. So to do that, our PI controller also needs a transfer function. So we can create a transfer function Kp plus Ki by S, and we can also simplify that in this form, which is a pole zero form of PI controller. And PI controller has a quantity called time constant of PI controller, which is nothing but a ratio of Kp or Ki. But now we have almost all transfer functions of the entire system. So the real world system can be represented this way, and I guess everybody is familiar with control system simplification. So all we need to do is block diagram reduction, or maybe you can apply some different complex advanced control techniques. Over here, an example is shown where all of this time of these blocks are very slow compared to the time constant of the machine, which is L by R time constant, which is in milliseconds. All of these sample times and PWM times are in the order of microseconds. Let us say switching frequency is 10 kilohertz, then sample time and PWM time is about 100 microseconds. L by R time constant of the machine is, let us say, 10 milliseconds. So this is huge compared to all others combined, and which is why we can take a lump of this, and the system, the PI controller is sensitive, so it can be faster or slower based on whatever time constant it can cancel. And the slowest pole, if we cancel, the response is faster. The slowest pole in this case is the motor's L by R time constant. So if we put the time constant of PI controllers 0 same to match at the same value of the machine's L by R time constant, it will cancel this pole. And if that does, then we can have at least initial design of the PI gain, at least the time constant value. Remaining time constants can be created as lump sum, and that represents the standard, in this case, a standard second order system, which is well analyzed in a textbook by Ogata. So please refer to it. A nice analysis is there, and based on different values of zeta, underdamped, critically damped, and overdamped, you can find the response of the system. I have taken critically damped here, and based on that, it allows us to find the value of the proportional gain. And this one gives us the integral gain because it's just a ratio of Kp or Ki over here. We find this PID gain, and all of this is also there. Like if you have MATLAB, you can run this script and you can find the analysis. You can find the transfer function of your motor And you can find the Bode plot of both uncompensated and compensated system, pole zero maps, stability analysis, and the predicted behavior of the system when you go for closed loop. Once this is satisfactory, you can just fix your PID gain or you can improve on it and go for the next part in the control system design, which is design of the speed controller. Speed controller is used by something known as cruise control and hill holding. Hill holding takes position control, but basically this is essential in implementing those features inside electric vehicle. To do this speed control, we have to at least assume that the current loop has settled down. The reference current has been reached by the PI controller. It is in steady state, which means that you have to allow at least four times the steady state delta time constant of the control loop. And we usually, generally, as a rule of thumb, take 10 times of the current loop's time so that reference current is reached by the current controllers and the remaining system components are placed here. The mechanical equation is converted into S domain, and that is also represented. Uh, and then we again do our block diagram reduction, and we try to design the speed controller. Now, if you look at the transfer function, you'll see that there are two zeros at origin for speed controller, this middle one. That means the system inherently starts at about 180-degree in phase, and which also means that any random value, usually it is trial and error, will push the system off the limits and it will make it unstable because there is zero phase margin available inherently in the system. So we have to do some complex math here also and try to find out zero of PI controller, which is before the pole of the next speed controller system, and that is done here. And that probably you can see here the system is starting from 180-degree phase margin. Because we designed a PI controller, it improves and allows a room for stability at the designed value of the controller, and it adds some phase margin, which is what we are designing for. 30, 40 to 60-degree is a typical value, but system is now stable and it will operate if we design a controller at this point. Pole zero map also confirms the stability, and then you can predict the response, and if it is satisfactory you can go for next step. Now all this is theory and it's fine, like everybody knows theory, but how do we actually go ahead and implement that in electric vehicle? So that is where engineering starts, and that is complex, and but most of us succeed at doing that. So let's get to it. So we take a real system. In our case, we are building a system for electric two-wheelers. So we have a BLDC two-wheeler motor, and there are plenty of them available in the market. We have to find the parameters. Systems engineering is extremely important here. If we get the wrong parameters, it's never going to work. The essential parameters are number of poles of rotor of the motor, back EMF value, the number of phases, and inertia, and all other parameters. Sometimes we have to conduct this thing. Then we require some inverter. This one is laboratory inverter, and then you can get something made by your own. So we also are trying to build our own inverters. You require a microcontroller to implement the control theory correctly. In this case, we are going to use Texas Instruments C283790 microcontroller, and then we require some software tools. So you can do either C programming or you can use the high level programming languages such as MATLAB and Simulink, which is what I'm going to talk about. Part of it is motor control block set. So I have been leading the design, and using this, customers are trying to achieve the targeted design much faster than what they thought of initially. Some examples are given, but we don't need to go there. What we are doing is we're going to take an example and we're going to run that motor which was there in the video. So how does it work is just simply you take a model inside Simulink, and you simulate that. If the results are perfect, the same model can generate C program that can be downloaded in this application board of TI, and it can be used to run the motor at different speeds. So this one is a low voltage laboratory motor, and Why do you require Simulink to design is because it helps you with simulation as first step, and then there is a lot of model-based design that allows flexibility and faster implementation. There are plenty of features, not just what I explained. So more features are also there. You can explore them in your free time. But we will talk about implementing this field-oriented control for now. We will be implementing that using Texas Instruments boards, and and all semiconductor companies have their development boards. So you can take any popular semiconductor. It doesn't need to be TI, but over here discussion is limited to TI. So they have multiple kits, kit 1, kit 2, kit 3, and you, depending upon whatever is available at your engineering college laboratory, you can take one of the kits and implement this. And here is a workflow. So what we do in practically implementing FOC is we have to first make sure that we can see properly the system. And how do we see the system? Through our eyes and ears. In terms of embedded systems, they are called sensors. So position sensor, current sensor, ADCs, whether they are working correctly or not, we will determine and we will calibrate them to make sure we are actually measuring 1 ampere current in real world when we see that through the microcontroller. That is called calibration. Second is we estimate the motor parameters. So these motor parameters which are obtained by the manufacturer may be correct, may be incorrect. That will have 10% variation from a system motor itself of the same model. So it's always better to conduct some experiments and measure the right parameters, because our control system design and stability of control system and depends entirely on getting this motor parameters right. That is how we are calculating the gains of the controllers. Once we have that, then we have to mathematically generate the model of both motor and inverter, then design the control algorithm. You can simulate and deploy on the hardware, and once it is fine, that is okay. Otherwise, you can iterate over the design until the right performance is achieved. So as I said, we'll be using this TI kit. It's very popular. You can Google it, or I can share the link with Professor Chirag after the session. This one is using a small VLDC motor, a small inverter, which is seen on top. This one, it's TRV8305. It's one of the popular driver by TI, and the bottom one is the microcontroller card. So what do we do by calibration of sensor is we connect the system, but we don't connect the motor, which means whatever you try to measure via the current sensors of the motor, it will always be zero since the motor is physically not connected. So when the motor is not connected, it will draw zero current, and that is what will be seen by the current sensor via analog to digital converters. We measure this. So at the room temperature, this count is different than the environmental temperature outside the lab. We have to measure this every day, or at least once in a week, and based on the electronics used, the sensitivity of the board, this will vary. But whatever is there, it is measured in terms of ADC output counts, and that is stored inside a variable. We can view that in oscilloscope, and we can find out the mean value that will be used by our programs so that we know where the 0 ampere comes. Next is we also need to what do you call scale the currents correctly. So for that we have to go through the circuitry for current sensors correctly, and we have to map the currents with real world amperes. But that's all about the calibration of sensor. How do we do it programmatically is that using model-based design, you can generate models like this one, and you can have an algorithm. So I think this is for position sensor calibration. I mentioned that we require the exact position of rotors, permanent magnets, north pole. How do we do that is one of the algorithm which is seen here is rotating the machine as 10% of its rated speed at a very, very low speed, and 10% of voltage is applied in something known as V by F control, voltage by frequency control. Machine will spin. At this time, the rotor north pole will come in align with the status rotating magnetic field, and we measure the position feedback. In this case, it's the Hall sensor. So the machine will spin at a very, very low speed, and its position will be measured, and we know that it is aligning with the synchronously rotating reference speed of the stator. We can we can do the comparison by the algorithm. And once the comparison is done, you know that okay, the position is offsetted by some value, and that is going to be fixed mechanically because the motor has been fixed and the position sensor is fixed on the motor. So every time it would be in this case zero point 0.2. All the quantities in this discussions are converted into something known as per unit system for motors, which is what a concept we have introduced. It's very popular for power system engineers to represent voltage, currents, and power levels. We are applying that for motors and embedded systems where the voltage is position, the quantity that represent the motor parameters, such as position in this case. Instead of representing that into radians or degrees, we are representing that in per unit. Likewise, for currents, all the full scale current of the motor is converted into work per unit. Rated speed of the motor is converted into base speed, which is 1 per unit, and that's how the program is implemented. And that is what also makes it scalable. So once the algorithm is decided, you can use it for different types of different power ratings of motors. Next is parameter estimation. So you can perform different tests in the laboratory manually on the machine to identify its parameters. And in parallel, you can use this algorithms what we have developed that requires some minimum inputs, some minimum information of parameters are required for the machine to run. So you input these parameters into the machine and then you configure the corresponding algorithm to work with your system. And once that is done, sorry about that, yeah, it will generate some programs and it will run this in real time inside your microcontroller and it will force execute this hardware tests that will measure the motor parameters such as measurement of motor resistance, stator resistance, that is as simple as Ohm's law. So we implement Ohm's law, we measure the motor current, we know the voltages, we can measure the voltages via this potential divider, and that allows us to measure the stator resistance. Then there is LD measurement, LQ measurement, there is back EMF test, there is retardation test. So all of these tests are done, and I think yeah, this. So it will be executed on the target motor. Uh, and there is a host model, which is a companion model that is connected with the microcontroller that talks with the controller via serial communication in real time. So that collects this feedback information and it displays the measured parameters. So the motor will undergo a couple of tests by these algorithms, which are specifically designed to implement this parameter estimation techniques. And once we have this, for example, back EMF and inertia, then we have identified the system correctly. The whole process is known as system identification. So we have identified the system correctly and we have all the parameters. So you can save them and then you can start working with them with the systems engineering team. So all of this can be saved. And I guess once it is saved, then you can import that into your simulation models as step one and try to simulate your real world motor into computers. So yeah, you can just load them and here there would be, you can view them. It would be just simple data structure. So anybody who's familiar with data structure, that is fine. Or you can also open in Microsoft Excel and view them. So that's all about parameter estimation. The next step is this, and yeah, you can also import parameters from your measured machine on the laboratory as well as motor design software such as ANSYS or Magnet. That is also possible. Once you have the parameters, you have to model the motor and inverter, and there are different fidelity levels of this modeling. So there can be average value model, which is required to do control system design, or there can be switching model, which is required to do inverter design. You want to do switching dynamics for capacitor placement or snubber design and all. And there can be different type of inverter as well, like modular multi-level inverter. So you can have different models and each model will have its own complexity. So starting with the average value inverter and motor model, this will implement all the math that we discussed earlier in the previous part. Now that math will use the measured parameters from motor, so that the representation of the system is as accurate to real world as possible. and we can find the real world representation. And the second part is switching model, where we use a different simulation technique. Instead of Simulink, we go to SimSkip, which is a causal simulation model, and it can mimic the switching dynamics of the inverter, and it allows the users to design a better inverter. At some point, you can put the various configuration of your devices, such as MOSFETs or IGBTs, various parameters such as RDS on state time, off state time, and analyze the behavior accordingly. And yeah, that's all. Once you are good, we go to the next part where we design the control system and tune the loop gain and verify the whole thing in the closed loop simulation. So how do we do that is we start with the speed controller from our concept of field-oriented control, where there is a speed PI controller, and then we go from there. The signals are taken to current controller. The real position feedback and current feedbacks are supposed to come from the hardware blocks. So that is what is being done here. Texas Instrument also has hardware accelerator for quadrature encoder thing, so that needs to be post process. So those blocks are doing that. And you can have different control algorithms: open loop control, closed loop control. Within closed loop control, there can be various types. So this one is field oriented control, where the feedback currents are processed through all the blocks that we discussed. And once that is done, your inverter will have some duty cycles that need to be generated so via PWM blocks. So this is going to be fed to the PWM blocks. And as far as the plant model is concerned, that would go into simulation. There is also a concept of variance, where like when you're simulating, it will only do simulation, and when you want to do code generation, all the plant model will be ignored by the program. And the control design, it resides into this function. So that function would be automatically called, and it will automatically design the controller for you. And if you want to do, you can also do empirical calculations of this PID gain. There is also an option of FOC auto tuner, and there is also an option of classical control theory. So that's all about control design. And yeah, when you open Simulink, you will find these models depending upon what system you want, Hall based or quadrature encoder based or different inverters. So you can download them from mathworks.com, and most of them would be there in your system already. So you can choose the type of inverter modeling fidelity, and you can simulate the model. This time, the model represents the real world system, and you can predict the behavior of the system correctly since the parameters are measured right. And as long as the parameters are right, you can compare within different fidelities of model. For example, the PWM one will have slightly different waveforms than the average value model. You can track reference speed with feedback speed, and then you can track the currents, which is in the second waveform for Q axis. Then you can check the voltage. So during startup, you can see in this particular case, the simulation runs in the open loop mode, because we want to mimic the real world system. Until the real world system controller receives something known as index pulse for quadrature encoder, it is kind of open loop for that. But once it receives that position feedback via index pulse of the quadrature encoder, it becomes possible for us to operate that in closed loop. Then you can analyze the PWM voltages and currents and behavior and the modulation technique and whatnot. So simulation allows us to look into this thing. If it is not going to work, we will know beforehand that okay, we have done something wrong. You can identify that beforehand, and you can iterate over it, and you can make it work. Now comes the exciting part. Like if it works in simulation, it is, since it is from a real world parameter of motors, it is 100% going to work on the motor if you have been doing things right until now. So that is what can be done. And if it is inside Simulink, inside any model-based design software, you can just right click and generate C code for the algorithm only, or you can export the entire model also. So to do that, instead of going to simulation, you can just find out whether it is configured correctly or not. The first one, which is being highlighted here, is the concept of sample time. So the algorithm is in different sample time. The rate one is 25 microsecond. Switching frequency in this example is 20 kilohertz, which represents 50 microsecond. That is same as our control sampling time, the green time. Speed controller works 10 times slower to that, so it has a 1 millisecond or 500 microsecond sample time. You see different sample times. There are different interrupts configured, so embedded system engineers would know what interrupts are. Based on these interrupts, we are having a scheduler and operating system designed that will execute our control program, and all of this simulation model will be converted into a C code that will be deployable on your embedded hardware. So you can also jump from the C code back into the model, iterate over it, get something right if you want to do that. Once it is done, there's also serial communication, which I explained earlier, that allows us to debug this in real time as the motor runs. So you can run this host model on your computer or laptop, and it will communicate with the microcontroller via serial communication. You can start, stop, and control the speed of the machine and observe the trajectory. So you can analyze the behavior, like whatever we tuned for in theory, is it going to work or is it not going to work? So, okay, it got paused. Sorry about that. And you can take the machine to different speed. So one represents the base speed over here in this machine, that is 4000 RPM. And you can check D axis current controller feedback, Q axis current controller feedback, currents for the stator in stationary reference frame, which is supposed to be sinusoidal currents. You can debug them. If there is something wrong, you will know here also. It's like kind of a oscilloscope or stethoscope for the motor. And once you are done, you can validate on the hardware. You can also do something known as profiling of the code, like how fast is the code compared to like what you would expect otherwise. So in this case, it has to execute in 20 kilohertz or 50 microsecond sample time, and it actually executes within 5 microsecond, which is a good thing. And for power electronics and embedded systems, we have to go sometimes in 1 millionth of a second or 1 microsecond. So this is even slow, but it is fine. Like 5 microsecond is much better for 20 kilohertz application. So this is good. And yeah, so at synchronous ties, we are trying to reach that sub 1 microsecond time frame by optimizing this algorithm blocks and all. So you can use these examples, and from MathWorks, if you're using MATLAB software, you have plenty of support available. That's all. You can post it on online community about all of equations for motor control and this thing. And yeah, as far as we are concerned, so we are trying to build similar software, and we are trying to automate the entire workflow with automated MATLAB simulations. Whatever we saw, that would also get automated soon. But yeah, so we can end the session for the time being here, and we can start taking questions and answers. I hope I'll try to, yeah, I think we have some time for questions and answers, so that is good. So yeah,
Uh, thank you. Uh, Participants, if you have any question, you can ask questions in chat box, or you can ask directly to our speaker. You can discuss with him also. Please raise your hand so our computer operator will unmute you.
MST, thanks.
Any questions? I hope you all are present or sleep down.
No, sir, thanks. Most informative class. Why not using PID? Yeah, there is a question on chat box, I think.
why not using in PID controller for design motor control algorithms?
Yeah, I can answer that. So PID is also popular. It is up to the user. Like you can use PID controller. In fact, what I was explaining in the FOC auto tuner example, go to that slide. And that is exactly what the FOC auto tuner does. So when I am manually designing, I'm more comfortable directly with PI itself. So why choose, like I sometimes remove integral controller itself. I just use P controller for certain applications. So it is totally up to the engineer. If you want PID controller, you can do PID controller. There are also two pole 2-0 controllers and complex controllers available. So when you are designing for your system, it's all up to you. So all this kind of simulating control design, whatever is seen here, or this FOC auto tuner, they use PID tune controllers. Um, and disturbance controller usually is required whenever there is too much of disturbance input. And in terms of motor control application, we don't have much of disturbance coming to the shaft of the machine. The only disturbance input will be slowly coming. That is when you're trying to go uphill. The load torque changes slowly, but that too happens within millisecond or seconds time frame, and that can be managed by PI controller itself.
There is another question. After successfully completing simulation, can we implement ready-made AI algorithm like cruise control, eco mode,
Of
sport
course, of
mode?
course, of course. So we have made that example also. Uh, Let me find out that. So whatever you want to do, you can just Google with MathWorks example and the relevant example along in this case. There are videos also explaining how to train your AI. This one is for reinforcement learning, but there is also neural network learning example. There is also reduced order model example. So you can apply various different AI techniques depending upon whatever research you are doing. So you just go to that page and it will, yeah, explain more. You can open the model and you can start right away. So you can do that. You can change your control techniques that is open. Mm. Uh,
Any questions? Which type control algorithm to adopt the BLDC motor in application regarding three-phase input supply?
yeah, so BLDC motors, they have six-step control. That is widely popular for low power applications where like there is a trapezoidal back EMF coming from the motor and you're just controlling the active phases via energizing any two phases at a time. This is known as commutation table for six-step control. You have the Hall feedback, and based on this ones and zeros of the Hall, you control the inverter switches Q1, Q2, Q3, Q4, Q6, two switches at a time, and it will dictate the direction of current as well as torque produced. So this is very basic and it's simple to implement also. Even like we have done this on Arduino. So it's that, yeah,
This
Arduino is
was
relatively slow for power electronics applications, but this kind of algorithms can be implemented on that.
Uh, I have one question, Darshan.
Yeah,
Uh,
please.
uh, means how it applicable in stochastic systems?
I don't know. I have to ask this AI what is stoichiometry? Stock.
Stochastic
it's random
random
variation.
random
Okay.
variation
Random variation on what?
On
means
The sum.
say
suppose
any parameter, torque,
suppose we
speed, so
consider noise in current voltage,
Mhm.
how it react.
Yeah, so that is it requires some more or disturbance rejection.
Yes,
So
Yes.
you have to update the control algorithm what we discussed into disturbance. There is also an example for that also. You can just search and you will find active disturbance rejection controller.
Mm.
You can try that. So based on the application, the entire thing gets modified. So this is instead of regular whatever we were seeing artificial neural network control, there is active disturbance rejection control. So
Rejection, yeah.
Yes.
you have to modify your system.
Yes.
So that is used to get like remove this noise from like this Kalman filter and all. They are used to
Mm.
reject the noise
Yes.
specifically. There would be an example. Yeah.
Another question. Why did you choose PMSM, not SRM for two-wheeler EV applications?
What
Yeah,
about
it can be
Appliances.
appliances?
used. Yeah. So it can be used. It's not like it cannot be used. It's just this slide which I was trying to mention. Efficiencies are different, and there are three parameters. So one is at the time of selecting motors for EVs. One is the volume, second is weight, and third is efficiency. So the efficiency is usually higher for PMSM compared to switch reluctance motor or synchronous reluctance motors until now. Some startups now are trying to build synchronous reluctance motors which are having same kind of volume, weight, and efficiency as a PMSM. That is still undergoing research. So if you are doing research in this area, please try to do that in a synchronous reluctance motor area because that is where our country has a huge requirement of reducing import dependency. These things are known as rare earth free motors. You can search
Mm.
them, and there are plenty of them. You can I can just yeah a little marketing for my startup. So there are plenty of rare earth free motors. So we are working on them right now,
Okay.
but it's okay. It's not that confidential. I can reveal them. But doing going rare earth free allows us to reduce import dependency, and that
Mm.
helps us. So you can consider other motors, but the motor manufacturer should be able to achieve the same performance as a permanent magnet motor in terms of specifically efficiency, weight, and volume. Yeah. So we are working
What
on all kinds of motors, by the way. Yeah.
Yeah,
Please go on. Sorry.
can see that.
what
Bearing
about
silence, bearing slice motor. I haven't heard this BSM,
No,
bearing
there are
slice motor.
crazy
What is it?
crazy kind of motors are being invented every day.
Yeah,
So people do a lot of research. So this one doesn't use bearings basically. All the motors
right.
have
But
mechanical bearing. It's somewhere between levitating duct fan, magnetic levitation, and a motor. So
okay,
yeah.
okay, that's quite a important thing because, I was lately working on bearing fault, because bearing is the biggest hurdle in all that motors, right?
So we remove that hurdle
The
itself.
faults, yeah, yeah, actually, the most mechanically affected part is bearing,
Yes,
right?
yes. So yeah, there is a research actively going on in this area, and there can be levitating motor basically.
Okay,
So some part is available on public domain. You can search for levitating duct fan by NASA, and that
levitating.
can probably give you some ideas about your research if you are interested in this area. But yeah, plenty of
It's
things are going
interesting.
on. Yeah.
Yeah, and one more simple question, maybe for you, actually. Yeah, we were working on this bearing faults. So in that case, we were you must have heard about MCSA, motor current signature analysis,
Yes,
right?
yes.
So how this EV, because the application requires lots of low speed, high torque, and all that. Uh, doesn't it mix up with the torque signature that are generally appearing on the input side of the current?
And that is why we chose field-oriented control. So that happens usually for BLDC control. A lot of torque
Mm.
fluctuations are there. Currents are not straightforward, constant. So, but yeah, that is so. If the currents are sinusoidal, most of the problems go away inside
Mm.
the
Exactly,
current
that's
signature
true.
analysis. Also, you'll only have fundamental current. That is
Mm.
what we are trying. There is something known as fault tolerant design where you can go on and analyze the harmonics of the currents. You can predict the faults. Bearing faults so far doesn't get big attention in EVs because they are inherently suppressed by the motor designer. As far as let's say this motor, this is our lab, by the way, at SVNIT. We are naming it
Yeah, I
Professor
can
KL
see
Arora Lab. This motor
that.
is a hub motor. It only has one bearing. And for the currents to damage the bearing, it requires a reverse path
Hmm.
which is available whenever it is uh, motor is an industrial motor that has two bearings at two ends.
Hmm.
So
Generally,
one
right.
bearing will have some current voltage introduced, and the rotor currents will find some local path through the second bearing. This can be removed in industry also via something known as insulated bearing. So one of the bearings you can use insulated and there won't be any current passed through it. So you don't require current signature analysis, but that helps in detecting mechanical wear and tear of the bearings.
Hmm.
So for EV industry, the vehicle you will expect that to run for 15 to 20 years, and maybe you will overhaul the motor
Yes,
after 5
exactly. And
years. So motor designers have to take care of the design itself so that you don't end up doing that. Industrial motors, they run for 24 hours, 365 days. So there, this problem is more prominent. But sooner or later it will come. Yeah, that is fair.
yes,
And yeah, I
any other
can
question?
show.
Advantages or
Yeah.
reasons for selecting doubly fed induction motor for EV applications.
No, that is one of the research area somebody is working on. So I also read this in. So one of the automotive companies investing heavily in that area. That is also they are trying to go rare earth free in Europe. Also, that is the trend going on because we can't expand as an electric vehicle industry if we are dependent on rare earth material. So this alternate research is going on. That's why you saw that doubly fed induction machine somewhere in the slides. But
But
I
is
hope that
is
answers. Yeah,
is motor a bigger hurdle or the batteries for the EV industry?
both. So battery
Okay,
also use a rare earth material called lithium,
exactly.
and motors use a rare earth. So these permanent magnets, they can be made by ferrite or they can be made by neodymium, iron, boron, samarium, cobalt. All these are rare earth metals, and they enable this reduction in size and volume. For instance, if you remember the loudspeakers which were used 20
Hmm.
years ago,
They
they
were
were really big in
magnets.
size, and now your small iPhone can also produce that kind of sound, and that
Hmm.
is possible only because of the magic inside that rare earth magnetic material. So it produces more magnetic field, and that allows us to reduce the size of the system. But yeah, if everybody adopts electric vehicles, we cannot get that forever. So that is why people are trying to research in other direction.
Okay. So any other question?
Yeah, by the time question comes, I can show the video of our this thing. So sorry,
Yes,
not
yes.
that. I
That will
can.
be more interesting.
So we are also creating our software for Indian companies who are trying to build their own electric vehicles. And of course, we are building our hardware. But yeah, it's okay. Right now, I have to probably find some others. I can go to. I keep the questions coming so I can share it. Yeah.
Yes, participant, you can write your question in the chat box if you want. Meanwhile,
So whatever I explained in the theory, our software, what it does is,
mhm.
sorry for the marketing, unintentional marketing, but we are building this software so that
No,
automates the
no.
entire theory that I explained. It automatically calibrates the sensor, identifies the microcontroller, programs that we have our own real-time operating system designed for that. Allows the users to speed up implementation of your control algorithm and run the motor at different operating points, calibrate sensors, tune the PID controllers if you want to do that manually and whatnot. So all this, and then it also is integrated with MATLAB. So if you want to simulate generate new simulation models. It will automatically create a model for you, simulate that, generate code, and modify the algorithm automatically.
That's great.
Over here, it is running a drive cycle test, which is required for electric vehicle industry, and you can analyze that. And as far as this workshop is concerned, since it is about AI, so I'll just give you a sneak peek about what we are working on. It's not open to you. So yeah, but so we have India's first AI search engine, uh, and it is right now working very similar to Google. So please give me next question. I'll feed that into our AI and we'll see what our AI does. So what
Please,
is the
Participant.
if anyone want to
What?
directly interact
Yeah,
with
there is a
our
question.
speaker, ah,
What what important about reference theory in WECs?
WEC?
Hmm.
What is WEC?
Yeah, please, Mr.
Senthil,
Senthil Kumaran. Please elaborate WEC.
WECS,
Wind energy
Wind Energy Conversion System,
Conservation. Okay,
conversion.
conversion.
conversion system.
What is important? So let's test our AI whether it can. So what it does is it does Google search for you. It tries to find out what, if the answer is available on the open internet, it will tell us. But yeah, let me also try to find out the answer. So yeah, wind energy conversion system mostly is the DFIG. Somebody also asked that question. That allows us to be synchronized with the grid and also convert the energy conversion, control the energy flow from wind into the available thing. So the DFIG machines are extremely popular for wind energy systems because the wind speed can change at any point of time, and the synchronous speed of electrically rotating frame is fixed by the grid voltages. So we cannot rotate the rotor at synchronous speed in the wind energy systems. But in order to get the maximum advantage, we require this control. And of course, field-oriented control itself is implemented there. So reference frame theory is there in order to simplify the complexity. There are three phases of stator winding which you need to energize, and three phases of rotor winding you need to energize and control. And since you would not be at synchronous speed, that would be known as arbitrary reference frame, or mostly I have seen rotor flux reference frame. So instead of going at synchronous reference frame of the rotating flux, you can be in the rotor flux reference frame and control the energy. And let's see what the AI has said. So it just applies more, converts into yeah, DQ frame, mathematical transformation. And yeah, it allows low voltage right through. So the AI is good. It found out something which I didn't know. So that is good thing. And yeah, so but without yeah the reference frame theory, it's extremely complex to do this for wind energy conversion systems. So if you have a follow-up question about something specific, just let me know. Yeah, we are just trying to do this. This AI is right now independent of motor controls, but maybe as we progress further, we will try to integrate the same within the control. Yeah. Okay, do we have next question? I think we're getting close to 9 o'clock.
Yes, please. If anyone have a question, please.
What about
Raspberry Pi.
uh, instead of PI controller in motor field control?
Hmm.
Raspberry Pi. Yeah, okay.
What about Raspberry Pi instead of PI controller in motor field control?
Yeah, so actually Raspberry Pi is a computer that has a microprocessor. And as far as implementing all these complex algorithms are concerned, like even whatever is the latest microprocessor that you may have seen, i9 Core i9 by Intel or some AMD processor or even NVIDIA's latest chip, they all are slow. for electrical engineers, they would understand and appreciate because you have to execute the program in microsecond. All of these controllers are so obviously Raspberry Pi is slow. It cannot directly do that. But if you want to implement Raspberry Pi, you can do something as simple as a six-step control, drive a BLDC motor. That is possible. Certainly, we have tried that. It allows you to do the flexibility of doing something known as IoT, Internet of Things. So, for example, we used our AI, so we can connect our AI with that BLDC six-step control using Raspberry Pi because it has peripherals that connects with LAN, and you can also generate PWM. So that gives that flexibility. But that is certainly not going inside the vehicle. It's going to be super slow. There are much faster and much dedicated options available. And I must actually, yeah, highlight that also. So the government is also supporting, if you are thinking in this line, there is something known as in this India Semiconductor Mission, which we are part of. And most of you are from educational institutes, so you would also be part of this via something known as Chips to Startup program via CDEC.
Hmm.
So just search for Chips to Startup and CDEC, and you can probably get access to the India Semiconductor Mission. If you're thinking of using something like Raspberry Pi, you can also create your own chips. Government wants that to happen, and they will support you. So that may be, yeah, of interest to some of you guys. But we require dedicated yeah, chips. The
Controller.
existing systems are too slow. Yeah. Yeah, let's go back. So there was another question about PI. I don't know. So, all right. Yeah. So actually
Yeah, I think,
huge,
yeah.
huge number of participation. So I appreciate that, and I also am thankful of your patience and listening. I hope I was able to do justice to the topic. Uh, yeah, even after the session, if you have questions, please feel free to drop them to our email ID or Professor Chirag and Professor Ravi. So they can
Sure,
also,
sure,
yeah, they can also try to get back to you.
sure.
Okay.
Oh,
So, thank you very much, Darshan sir. It was a very, very informative session, and I believe that those who have attended must have got a lots of uh, feeling. Basically, I would say that how I think there is one. Yeah. Okay. So we thank Darshan sir for this very insightful session. And if you have any question, you can drop a message to me or Ravi sir. We will get back to Darshan sir and we'll try our best to give you that response possible. Thank you very much, Darshan sir. I think we should end up the session today.
Yeah, I just want to close one question I saw noticed in the chat. So Parthiv Bhatt
Sure.
asked that he's asking that which motor is better for EV, switch reluctance motor or synchronous reluctance motor? So that is definitely synchronous reluctance motor. The operating principle of switch reluctance motor is similar to BLDC, and it produces less torque compared to synchronous reluctance motor, but it also depends on the motor designer. How do you design the machine?
You choose PMSM, not SRM. Why did you choose PMSM, not SRM for two-wheelers? I think that answer was given, right?
given,
I
given.
think,
Yeah.
yeah. I think all the answers are given.
All
Yeah.
questions, all answer
Hmm.
given.
Okay. Okay. Yeah. So we can wind up now. Thank you,
Yeah, we can
everyone.
wait.
Okay.
Yeah. Thank you for the
Okay,
Okay, thanks
opportunity.
again.
participants. We meet again tomorrow at same timing.